The wheels touch the runway, 300 tons, moving at 270 kilometers per hour. The tires compress under a load that would crush a car flat. Smoke bursts from the contact point. Not a malfunction, not a problem. Physics. And now, the clock starts. Because in the next 30 seconds, every single joule of kinetic energy carried by that aircraft must be converted into something else. Heat, sound, friction, reversed thrust, all of it, in 30 seconds, on a strip of concrete less than 3 kilometers long. Look at the numbers for a moment. A fully loaded Boeing 737-300ER at maximum landing weight, 251,000 kilograms. Landing speed, approximately 265 to 280 kilometers per hour. The kinetic energy of that aircraft at touchdown, the raw energy that must be dissipated before it reaches the end of the runway, is approximately 700 megajoules, 700 million joules. That is roughly the energy released by detonating 150 kilograms of TNT. All of it. Absorbed, converted, neutralized in less than 30 seconds. And you did not feel it. You felt a firm touchdown, a rumble through the seat, the pressure of deceleration against your chest. But the engineering that made that possible, the layered, sequential, precisely timed system that absorbed 700 megajoules without destroying the aircraft, is one of the most demanding mechanical challenges in all of transportation. Here is what almost no passenger understands. The wheel brakes are not the primary braking system. They are not even the first system to activate. By the time the brakes are doing their maximum work, two other systems have already been operating for several seconds and have already eliminated a significant fraction of the aircraft's kinetic energy. An aircraft does not stop like a car. It stops like a controlled energy dissipation sequence in which every system activates at a specific moment in a specific order, each one creating the conditions that allow the next one to work. Miss any step, activate any system out of sequence, and the stopping distance increases, sometimes by hundreds of meters. Let's go through that sequence. The first system activates before the wheels ever touch the ground. It is the wing itself. During the approach, the aircraft has already been shedding speed aerodynamically for several minutes. Flaps are extended to their maximum landing setting. On a Boeing 737, that is typically flaps 30 or flaps 40. On a 777, flaps 30. Full flap extension dramatically increases drag. The wing, reshaped into a high-lift, high-drag configuration, is already fighting the aircraft's forward motion before the runway is ever reached. This is not incidental. It is the first stage of braking, beginning in the air, miles before touchdown. The lower the airspeed at the moment of touchdown, the less kinetic energy the ground-based systems must absorb. Every kilometer per hour shed in the air is energy the brakes do not have to handle. The second system activates within fractions of a second after touchdown. Spoilers. On the upper surface of the wing, a series of large panels hinge upward simultaneously, either automatically through ground spoiler logic or commanded by the crew. Their primary function is not aerodynamic braking. It is lift destruction. At 270 kilometers per hour, the wing is still generating a substantial fraction of the aircraft's lift. That means a substantial fraction of the aircraft's weight is still being supported by aerodynamic force, not by the landing gear. Weight on the landing gear equals braking force. Weight supported by the wing equals zero braking force. Spoilers destroy the wing's lift instantly. The full weight of the aircraft transfers onto the landing gear. Tire-to-runway contact force spikes. Braking effectiveness multiplies. Without spoilers, the wheel brakes would be operating on a fraction of their potential friction force for the first critical seconds after touchdown. With spoilers deployed, the brakes immediately have access to the full normal force of a 251,000 kilogram aircraft pressing down through 8 main landing gear wheels. This is the foundation that makes everything else possible. Now, the third system. Thrust reversers. The engine nacelles change shape, change. Blocker doors or cascade vanes deploy inside the engine nacelle, redirecting the exhaust flow forward instead of rearward. The engine is still producing thrust, but that thrust is now directed partially against the direction of travel. On a 777 with two GE90 engines, each engine producing 110,000 pounds of forward thrust at takeoff, reverse thrust can generate a meaningful deceleration force in the first 15 to 20 seconds after touchdown when the aircraft is moving fastest. This is the critical point about thrust reversers that is almost universally misunderstood. Reverse thrust is most effective at high speed. Its contribution drops rapidly as speed decreases. Below approximately 80 knots, reversers contribute relatively little to deceleration, and most operators reduce or cancel reverse thrust at that point. This is why thrust reversers are used aggressively in the first seconds after touchdown, while the aircraft is still fast, and then phased out as the wheel brakes take full authority. On a dry runway under normal conditions, thrust reversers contribute approximately 20 to 30% of total stopping force during the high-speed phase. On contaminated runways, wet, icy, snow-covered, their contribution becomes proportionally larger because wheel braking effectiveness is severely degraded by reduced friction, while reverse thrust remains unaffected by surface conditions. This is why, on a slippery runway, you will hear the engines roar into reverse with noticeably more aggression than on a dry summer landing. The pilots know the math. Now, the fourth system, and the one that does the heaviest work: wheel brakes. On a modern, wide-body commercial aircraft, the main landing gear typically consists of two body gear bogies under the fuselage and two wing gear bogies under the wings, each bogie carrying multiple wheels. A 777 has a total of 14 main gear wheels, each equipped with a multi-disc carbon brake assembly. Carbon brakes replaced steel brakes on commercial aircraft beginning in the 1980s for a specific combination of reasons. Carbon composite material can absorb far more energy per kilogram than steel. A carbon brake assembly weighs approximately 40% less than an equivalent steel assembly. Carbon maintains its structural integrity at temperatures that would cause steel brakes to fade, warp, or fail entirely, and the temperatures reached during a maximum energy stop are extreme. During a full energy rejected takeoff, the certification test in which an aircraft accelerates to V1 decision speed and then brakes to a complete stop without using thrust reversers, brake temperatures routinely exceed 1,000 degrees Celsius. At that temperature, the brake assembly glows red-orange. The surrounding structure reaches temperatures that can ignite tires and hydraulic fluid. This is why, after a rejected takeoff or a heavy landing stop, aircraft are required to hold on the runway or taxiway for a defined cooling period, sometimes 30 minutes or more, before being cleared to taxi to the gate. Brake temperature is monitored continuously through sensors in the brake assembly displayed on the cockpit's brake temperature monitoring system. Takeoff with brakes above a defined temperature threshold is prohibited because brakes that are already hot cannot absorb the energy of a subsequent rejected takeoff. The certification requirement for brakes is absolute. The aircraft must be able to reject a takeoff at maximum weight at V1 and stop safely on the runway using only the wheel brakes. No thrust reversers, no aerodynamic drag devices. Thrust reversers are not certified as primary stopping systems. They are performance credit, energy reduction that reduces the load on the brakes and shortens the stopping distance. But the aircraft must be able to stop without them. Now let's talk about the control system that manages the brakes during this entire sequence. No human can precisely modulate brake pressure across 14 wheels simultaneously at deceleration rates exceeding 0.4 G, with each wheel responding differently to local runway surface variations. The system that does this is autobrake. The flight crew selects a deceleration target before landing, typically expressed as a deceleration level from 1 through max, and the autobrake system maintains that deceleration rate by modulating hydraulic pressure to the brake assemblies throughout the stopping roll. The system calculates required brake pressure from current ground speed, aircraft weight, and runway conditions. It applies more pressure when deceleration drops below the target. It reduces pressure when deceleration exceeds it. This produces a smooth, consistent deceleration profile, rather than the oscillating, inefficient braking a human pilot would produce manually. Beneath the autobrake system sits the anti-skid system, the aircraft equivalent of automotive ABS, but operating at significantly higher sensitivity and speed. Each wheel has a speed sensor. The anti-skid computer monitors all wheels simultaneously. The moment any wheel begins to decelerate faster than the others, indicating the onset of a skid, the computer reduces hydraulic pressure to that wheel within milliseconds. A locked wheel on a 270 km/h aircraft does not produce maximum braking force. It produces a flat spot on the tire, eliminates directional control through that wheel, and generates a patch of superheated rubber that reduces friction rather than increasing it. The anti-skid system prevents this by keeping every wheel operating at the optimal slip ratio, the point at which the tire is rotating slightly slower than ground speed, maximizing friction without locking up. On a wet runway, the anti-skid system operates at the boundary between controlled braking and aquaplaning, the condition in which a film of water completely separates the tire from the runway surface, eliminating friction almost entirely. Aquaplaning speed on an aircraft tire at full landing weight begins at approximately 195 times the square root of tire pressure in psi. For a typical airliner tire inflated to 200 psi, aquaplaning can initiate above approximately 200 km/h, well within the normal touchdown and initial rollout speed range. This is why runway surface texture, drainage design, and crosswind components are all calculated before every landing, and why landing distance in heavy rain can increase by 60% or more compared to a dry runway. The runway itself is the final element of the stopping system, not simply a surface to roll on, an engineered deceleration platform. Grooves cut transversely across the runway surface channel water away from the contact patch and maintain tire-to-surface friction in wet conditions. And the stopping distance increases, the margin shrinks, the runway end approaches faster. The 30 seconds you feel as a mild deceleration is the output of an engineering sequence calculated to tolerances measured in meters on a surface measured in seconds. It is not stopping, it is controlled energy elimination. And every landing you have ever made depended on every part of that system working exactly as designed. If you want to understand what happens when one of those systems fails, when a rejected takeoff goes wrong, when brakes overheat on a short runway, when the anti-skid system has nothing left to work with on ice, I've covered that in another video,